This line turns old cables into near pure copper again, not with magnets but with air separating by density. Drift one airflow set point, and copper rides with plastic into the wrong stream. The control is not in the granulator. The control lives inside the air classifier. Let's step into the line. This is not metal versus waste. It is profit versus loss. Misgrade and copper is downgraded, reworked, or sold at a discount. Because the line runs non-stop, tiny drift becomes tons of loss fast. Downstream, wire makers need copper that melts and casts predictably every time. That predictability starts here, long before any furnace sees the material. We will track 6 stages through one continuous line, from feed to verified outputs. First, intake and cutting stabilizes feed geometry for the machines. Second, granulation liberates copper from insulation into separable particle shapes. Third, the air classifier makes the main split using drag and terminal velocity. Fourth, vibrating tables polish the last percent and stabilize purity. Fifth, copper testing verifies grade, conductivity, and hidden contamination. Sixth, plastic pelletizing turns insulation into reusable feedstock, not disposal. The process identity is simple. Closed-loop cut-point control in moving air. Cable scrap arrives mixed, tangled, and inconsistent in construction and stiffness. Some loads are thick conductors, others are fine strands, and many are mixed together. Before separation works, variability must be reduced into a feed the machines can predict. That starts with opening bales, removing trash, and stabilizing how material flows. Cutting looks basic, but it decides whether separation can ever be clean. Downstream machines need a repeatable bite size and repeatable feeding behavior. Long pieces bridge across conveyors and surge into the granulator and pulses. Too short, and you create fines, dust load, and unstable air behavior later. So the target is not small, but repeatable, and repeatable under real variability. Rotary knives cut cable into uniform segments for steady feeding. Operators watch feed behavior because bridges and surges always show up early. They also watch motor load because torque spikes signal tangles and stringers forming. A frayed copper plastic bundle behaves like a sail, even if it contains copper. If cutting produces sails, the classifier has to solve a geometry problem. Stringers bypass separation and carry copper into the wrong stream. That loss looks invisible because input mass still matches output mass, but value leaks out when copper follows plastic into a low-value fraction. So stable cutting protects yield before any air set point even matters. Now the feed is stable, but copper is still trapped inside insulation. Liberation is next, and liberation is where the real separation begins. Granulation is not shredding, it is controlled particle liberation. The goal is copper and insulation exiting as distinct particles, not wrapped bundles. If copper stays partially sleeved, it behaves like plastic during air separation. If granulation makes too many fines, recoverable copper becomes dust-like and mobile. So the granulator must cut cleanly, inside a size band the classifier can handle. High shear cutting frees copper, while screens limit maximum particle size. Knife geometry, screen openings, and cutting sharpness define the outgoing particle mix. Operators track amperage trends because load changes reveal cutting quality in real time. Clean cutting yields compact copper granules and flatter insulation flakes. Dull cutting smears insulation onto copper and increases borderline mixed particles. Those borderline particles are where the cut point becomes expensive. Knife wear increases smearing, and copper starts behaving like light fraction. If you later see copper in the light stream, the granulator already failed here. Maintenance is not separate from separation. Maintenance is a separation control action with direct yield consequences. With liberated particles, the line can finally sort by physics, not by hope. Now we reach the box that decides everything: the air classifier. Most people expect magnets here, but copper is not ferromagnetic. Instead, the separation is aerodynamic, based on drag and terminal velocity. Dense particles fall against an upward airflow, while light flakes ride the flow. The key detail is this: the classifier is not passive. This box is a control device because the cut point can move with drift. Copper has a density of about 8.96 grams per cubic centimeter, which resists lift strongly. Many insulation plastics are far lighter, often around 0.9 to 1.4 grams per cubic centimeter. That density gap is real, but density alone is not the whole decision. Drag depends on surface area and shape, not just on mass. Flat flakes behave like parachutes, while compact granules behave like stones. So the classifier must be tuned for a mixed population of shapes. Upward air creates a cut point where only light particles stay suspended. The channel geometry forces repeated decisions, sharpening the split over multiple passes. In practice, the cut point is a narrow corridor, not a single perfect boundary. Small shifts in airflow move that corridor and reclassify the borderline particles. That is how copper can follow plastic without any obvious mechanical failure. Airflow drift shifts the cut point, sending copper into the light stream. One drift does not make a bad bag. One drift can ruin an entire shift's worth of recoverable copper value. This is why the control is in the air classifier, not the granulator. Granulation creates the particles, but airflow decides the grade every second. Even when the split is stable, polishing still matters for final purity. After air separation, the heavy stream is mostly copper, but not finished copper. Light contamination remains, especially when particle shapes overlap at the margins. Vibrating tables provide a second density polish using controlled stratification. They separate by how particles settle and migrate across a vibrating deck. Vibration stratifies by density, sending heavies one way and lights another. Deck angle, vibration energy, and feed rate control the stability of that stratification. Operators adjust in small steps because polishing is sensitive to loading changes. This stage is where the last percent gets removed or carried into final copper. It is also where gradual drift is dangerous because it looks like normal operation. Table drift leaves light contamination in the copper concentrate. The last percent is where spec failures begin, not where they end. Polishing protects the next stage because testing should confirm, not discover surprises. Now we can name the hidden system that keeps the split stable over hours. It is not a single machine, but a control loop wrapped around moving air. The hidden mechanism is a closed loop that holds the cut point stable. Airflow changes with dust load, filter restriction, and shifts in feed composition. So you cannot run the fan at a fixed speed and expect stable separation. Instead, the line treats airflow as a controlled variable tied to product outcomes. The process identity is simple. Closed loop cut point control in moving air. A drive adjusts fan speed to maintain stable separation behavior under changing load. Pressure signals indicate restriction and loading inside ducts and collection equipment. When restriction rises, uncontrolled systems lose effective airflow and blur the split. Controlled systems compensate, then verify the result with repeated sampling. That loop turns a separator into a predictable production tool. It also turns airflow tuning into the yield valve for copper value.